Hello everyone, welcome back to another lecture video on design of machine elements. In this video, we will be talking about the theories of failure or why we need theories of failure. So before that, I would like to mention theories of failure are some criteria or governing conditions which are used for designing components which is subjected to complex loading. So when I am saying the design of components subject to complex loading, then how we are designing the components subjected to simple loading. So for explaining that, I am considering a simple tension test which is conducted on UTM. So here the specimen will be kept between the two jaws of the UTM machine, and which is having a movable jaw and fixed jaw. So whenever I am moving one jaw, it will be applying some force on the specimen and a reaction force will be developed at the other fixed end. So you can construct the member load diagram. So member will be drawn in this way and load P will be marked in this one, and this will be creating a uniaxial loading, for which I will be constructing the element stress diagram from this member load diagram. So if you are considering the member force diagram, in that I will be considering this element, rectangular element. So this is uniaxial loading which will be creating axial normal stress, and that value will be sigma equal to P by A. So this is showing the element stress diagram for this one. So using this one, I am conducting the simple tension test, and whenever I am applying the load P or increasing the value of load P, the stress will be increasing. So by taking these values of loads which are acting at different instance, and by measuring the deformations or the extension in length that is happening for this specimen, I can have the load and deformation. So from load and deformation, I will be finding the stress and strain, so that I can construct a stress strain diagram for this one. So from simple tension test, this stress strain diagram is showing the curve which is made for a ductile material. Ductile material is which only having the predominant plastic deformation. So this stress strain diagram, these salient points you are knowing. So in this one, if you are increasing the load, this will be having a point which is known as yield point, from which further increase in load will be causing the material to deform plastically. So while designing some components, we will be defining some criteria as the material will be failing if it starts to deform plastically. So for ductile materials, the criteria or failure limit will be set with respect to the yield strength value. So if you are looking on this curve, for a ductile material, the elastic, this curve is shown, the stress strain curve, and this value sigma yield will be taken as the limiting condition for design of such ductile materials. So if you are having a brittle material, it will be having a stress strain diagram shown by this green curve, and that they will not be having the plastic deformations. They will be finally failing without showing any signs of plastic deformation, and that ultimate point or the sigma ultimate strength will be used as a design criteria for brittle materials. So while designing, we will be using sigma yield and sigma ultimate as the properties for designing this ductile and brittle. And I have mentioned these values are obtained from simple tension test conducted on UTM, where the load acting is uniaxial. So here these are the properties obtained from simple tension test, which is uniaxial loading. So I can use these properties only for design of components which are also subjected to similar loading. That means this criteria can be used to only for components subjected to uniaxial loading. So I will be showing an example. So here a solid shaft is given which is subjected to an axial load of 30 kilonewton, and here we have to determine the diameter of the shaft required if the yield strength of the material is 350 megapascal. So it is a ductile material and its yield strength sigma yield is given which is 350 megapascal. So this 350 megapascal yield strength is obtained from simple tension test, which is uniaxial loading, and here also a shaft is subjected to uniaxial loading. Here both the conditions from standard test is uniaxial, and here the component is also subjected to uniaxial loading. So I can directly compare these conditions. So first I will be drawing the this image is blurred. Anyway, you can read out these things. So this is the shaft subjected to load 30 kilonewton, which is axial, which will be creating axial normal stress, and you can evaluate the stress induced as load by area 30 into 10 raised to 3 by pi d square by 4. So this will be where d will be the unknown which we have to solve. And this is the stress induced, and the property of the material is also given, which is sigma yield, which is 350 megapascal or 350 into 10 raised to 6 pascal. So you are having the stress induced and the strength of the material. So you can directly compare as both of these loading conditions are uniaxial. So you will be equating both of this for the limiting condition. So you can find the diameter after solving this one, which you will be getting as 0.01044 meter, which is equivalent to 10.44 mm. So this problem you can solve easily as both loading conditions are similar. From standard test you are having uniaxial, and for the loading given in this problem is also uniaxial. But what if the machine component is subjected to a complex loading, 2D or 3-dimensional? Here a 2-dimensional loading is shown where sigma x, sigma y and tau xy loading is applied. So here which one you will compare with the sigma yield if it is a ductile, or sigma ultimate if it is a brittle material? So that is the problem. So here which one you will compare? Is it sigma x or sigma y or tau xy? So you cannot directly compare any of this with these properties, because this loading is not uniaxial, where these properties are obtained from the simple tension test where uniaxial loading conditions are prevailing. So we will have to formulate some theories of failure. That is the need for formulating theories of failure. You cannot directly compare the conditions that are happening for a machine subjected to complex loading with the properties obtained from a uniaxial loading simple tension test. So therefore we need to some theories of failure, and we will be discussing this major 5 theories of failure. One is maximum principal stress theory, maximum shear stress theory, maximum principal strain theory, maximum strain energy theory, and last one discharge energy theory, or it is also known as maximum shear energy theory. So in next video we will be explaining these theories of failure, or these 5 theories one by one. So thanks for watching.